Good day and welcome to our next lesson. In this video, we will be discussing the basics of mass transport. Particularly, we will be discussing steady-state diffusion. So let's start with the lesson. Let's first have a brief introduction to mass transfer. So by this point, you have already passed momentum transfer and heat transfer, and mass transfer is the third transport phenomena. Mass transfer is the net transport of molecules from a region of high concentration to a region of low concentration. By this point, you are already familiar that the driving force to mass transfer is the difference in concentration, because a particular species would spontaneously transfer from a region of high concentration to a region of low concentration. Mass transfer is widely studied because of its wide array of applications from gas-liquid absorption, leaching, liquid-liquid extraction, humidification, and many more. We have two mechanisms of mass transfer. We have diffusion and convection. We will be discussing diffusion in this lecture and convection in a separate lecture. Diffusion is analogous to conduction in heat transfer, while convective mass transfer is analogous to convective heat transfer. Since we have established an analogy between heat and mass transfer, we can also say that diffusion mass transfer is slow but orderly, and that is in contrast with convective mass transfer, which is fast but chaotic. That is because convective mass transfer normally involves turbulence in order to have a very fast rate of transfer of mass. Let's start with diffusive mass transfer. The main governing equation for mass transfer is called Fick's law. It is analogous to Newton's law in momentum transfer and Fourier's law in conduction. We have here a generalized equation of Fick's first law. NAZ is called the molar flux of A along the z direction. Take note of the subscript. That is equal to negative DAB. DAB is the mass diffusivity of A on B. Take note that we have two subscripts on D. That's because for this instance, we are saying that substance A is diffusing through substance B. Okay? And that mass diffusivity is multiplied by dCA over dZ, in which Ca is the molar concentration of species A, and Z is the distance between two reference points. This Fick's first law can also be written on this second equation here, that is negative C times dAB multiplied by dXA over dZ. X sub A in this case is the mole fraction of substance A, and C is the total concentration of the system. That's because total concentration multiplied by the mass fraction gives you the concentration of the particular species. Fick's law can also be written in terms of mass unit as written in this equation below. We have JAZ is equal to negative DAB multiplied by d rho A over dZ. When you see the variable J, this pertains to a mass flux. So we are now differentiating the use of the letters N and the letter J. We use the letter N for molar flux. We use the letter J for mass flux. Okay, for the mass version of Fick's first law, our gradient is expressed in terms of the mass density, that is rho A, with respect to position. We can also write this as JAZ is equal to negative rho times DAB over d omega A over dZ. Omega A is the mass fraction of species A, and rho here is the total mass density of the system. Let's proceed. What we have here is the generalized equation of Fick's first law, which includes the effects of bulk fluid motion. Bulk fluid motion means that we are considering the entire body of the fluid. Okay, so we have the equation NAZ, or the molar flux of species A, is equal to negative C dAB dXA over dZ plus X sub A multiplied by NAZ plus NBZ. NAZ is the molar flux of species A, and NBZ is the molar flux of species B. This equation is applicable for a binary system, meaning we have two substances in our system. The term XA, NAZ plus NBZ, represents the molar flux resulting from the bulk flow of the system. Okay? In some cases, we can neglect this term. In some cases, we need to simplify this into a more manageable equation. Because if you notice, NAZ appears on both sides of the equation, thus it is not explicit. We will be discussing some of the limiting conditions in diffusive mass transfer in order for us to simplify this equation. The first limiting condition is called equimolar counter diffusion, or ECD. Equimolar counter diffusion is a limiting case of binary diffusion wherein both components respond to a concentration gradient and thus have the same rate of diffusion, only opposite in direction. We can imagine equimolar counter-diffusion through the use of this diagram here. So assume that we have two boundaries. One is denoted as Z sub 1 and the other is denoted as Z sub 2. Z sub 1 is on your left, Z sub 2 is on your right. You would notice that for Z sub 1 or on your left, the concentration of A is high, while on your right, the concentration of A is 0. The reverse of that is true for B. The concentration of B is high on your right, and the concentration of B is 0 on your left. So based on the principle of mass transfer by diffusion, your species would transfer from a region of high concentration to a region of low concentration. So for species A, we are expecting them to travel from left to right, and molecules of B will be traveling from right to left. Okay? Now, for equimolar counter-diffusion, we are saying that the rates of diffusion of A and B are equal, but they are of opposite signs. That's because Na sub Z is from left to right, indicating a positive sign, while NBZ is from right to left, indicating a negative sign. So NAZ is equal to NBZ, but in our diagram, NBZ has a negative value. If we go back to our general equation of diffusion, we have NAZ is equal to negative C DAB dXA over DZ plus X sub A times NAZ plus NBZ. Now, based from our understanding of equimolar counter-diffusion, we say that NAZ is equal to negative NBZ. Therefore, we can also say that NBZ is simply equal to negative NAZ. We can substitute this to our general equation in order for us to simplify this equation, and this will just be in terms of NAZ. We have NAZ is equal to negative C DAB dXA over DZ plus X sub A times NAZ minus NAZ. We are substituting NBZ to negative NAZ. So as you can see from the substitution, NAZ would cancel. We would be left with the equation NAZ is equal to negative C times DAB times dXA over DZ. Or this is the most basic form of Fick's first law of diffusion. Okay, so for equimolar counter-diffusion problems, we will be using this form of Fick's first law. If we go back to our PowerPoint, you would see that we have obtained the molar flux equation for equimolar counter-diffusion. Next case, we have unimolecular diffusion or unimolar diffusion. Unimolar diffusion is a special case of binary diffusion where a diffusing species A moves through a stagnant fluid B. So for the previous equimolar counter-diffusion, both species A and B are moving at the same rate but at opposite direction, while here for unimolar diffusion, species B is stationary and only species A is moving. Since species B is stationary, we can say that the molar flux of B is equal to 0 because it's not moving. So if NBZ is equal to 0, let us derive the resulting equation for unimolar diffusion coming from our generalized equation for diffusion. If species B is stationary, therefore NBZ is simply 0, we simply cancel this term and we will be left with NAZ is equal to negative C DAB dXA over DZ plus XA times NAZ. We can now transpose the second term of the right-hand side of the equation to the left-hand side of the equation, giving us NAZ minus X sub A NAZ is equal to negative C DAB dXA over DZ. Extracting NAZ, we have NAZ times 1 minus X sub A is equal to negative C DAB times dXA over DZ. This gives us the final form of the equation NAZ is equal to negative C DAB over 1 minus X sub A times dXA over DZ. This is our simplified equation for the limiting condition of unimolar diffusion. If one of the species is stagnant, you may use this equation. Now take note that in this differential equation, we have the variable x sub a appearing on the right-hand side of the equation. That means that when you integrate this expression, this would result to a natural logarithm because you have dxa over 1 minus xa. Okay? We will be integrating this later in our example problems. So those are our two limiting conditions for steady-state diffusion. Again, we have equimolar counter diffusion and unimolecular or unimolar diffusion. Let's now move through pseudo-steady-state diffusion. So pseudo-steady-state diffusion is very useful for us if we want to solve problems that are technically unsteady-state problems, but we don't want to go through the hassle of looking at Bernoulli charts in order for us to solve it as an unsteady-state problem. For simplification purposes, for a specific period of time, we are going to assume that the rate of diffusion is constant such that we can apply the pseudo-steady-state diffusion solution. For example, let's consider a glass of water, pictured here, that is evaporating at steady state. For small changes in z, wherein z is the water level, we can consider the molar flux to be constant. Therefore, the molar flux of the evaporating species can be expressed in this equation. We have NaZ is equal to rho A over Ma times dz over dt. Rho sub A is simply the density of substance A. M sub A is the molecular weight of substance A. Now, let's try to derive the expression for time elapsed under pseudo-steady states unimolar diffusion conditions. For this derivation, we will be starting with our equation for unimolar diffusion. This is what we have derived earlier. Before we can integrate, we simply have to separate the variables. Separating, we have NaZ multiplied by dz is equal to negative C dAB times dxa over 1 minus xa. Integrating both sides of the equation, we have NaZ multiplied by z. That's equal to negative C dAB multiplied by ln of 1 minus xa. Multiplied by negative 1 to satisfy the chain rule, so the sign would now become positive. Okay? And we are integrating this from xa1 to xa2. We will not be substituting the limits for z yet because we will be using this equation in our pseudo-state diffusion derivation. Substituting, we have NaZ is equal to positive C dAB over z times ln of 1 minus xa2 over 1 minus xa1. This derived equation for unimolar diffusion can now be substituted into our pseudo-steady-state diffusion equation. Since they are both equated to NaZ, we now have the equation C dAB over z times ln of 1 minus xa2 over 1 minus xa1 is equal to rho A over Ma multiplied by dz over dt. We can then again separate the variables such that all of the z terms will be on our right and all of the t or time terms will be on our left. So we have C dAB ln of 1 minus xa2 over 1 minus xa1 multiplied by dt is equal to rho A over Ma multiplied by z dz. Integrating a second time, we now have C dAB multiplied by time multiplied by ln of 1 minus xa2 over 1 minus xa1 is equal to rho A over Ma is simply a constant, and then the integral of z dz is equal to z squared over 2. We will be integrating this with our limits from z1 to z2, wherein z1 is our liquid level at time is equal to 0, and then z2 is our liquid level at time is equal to t. Okay, let me first erase this part about unimolar diffusion. Simplifying, we have C dAB t ln of 1 minus xa2 over 1 minus xa1 is equal to rho A over Ma times z2 squared minus z1 squared all over 2. Now, let's simplify this equation and solve for time. Because for pseudo-state diffusion, most often we will be solving for the time elapsed for the liquid to go down from level Z1 to level Z2. Okay? Solving for time, we now have On our numerator, that is rho A times Z2 squared minus Z1 squared. On our denominator, we have 2MA, C, DAB, and ln of 1 minus XA2 over 1 minus XA1. This is now our expression for the time elapsed under pseudo-steady state conditions. Okay, we will be making use of this derived equation in our example. With that derivation, let's now try to solve some examples. First example, refer to the figure given. This is an example of a vapor degreaser setup. Given a cylindrical tank containing trichloroethylene or TCE with its level maintained at 0.2 meters and temperature maintained at 35 degrees Celsius. TCE has a molecular weight of 131.4 grams per mole, a vapor pressure of 115.5 millimeters of mercury, and diffusivity in air of 0.088 square centimeter per second at the given temperature. Current regulations state that the degreaser cannot emit more than 1 kilogram of TCE per day. Determine if the degreaser is in violation of this regulation. If you take a look at our illustration of the degreaser tank, you have here your Z1, or the level of the liquid that is maintained constant at 0.2 meters. The liquid TCE is maintained at 35 degrees Celsius. And since our TCE vapor is being produced at this Z level, in which Z1 is equal to 0.2 meters, the TCE vapor has to diffuse through air that is stagnant in order for it to travel to the top of the drum. Okay? So we have here represented our second point, Z2. That is, Z2 is equal to 5 meters because the tank is 5 meters tall. Now, you might have noticed that YA2, or the mole fraction of TCE vapor in the air at this level of Z at the top, is equal to 0. Why is it 0? That's because we are assuming that if the TCE vapor passes through this threshold, it will just be carried away by a very, very large volume of air such that its concentration is now assumed to be 0. Okay? Therefore, our driving force will be between YA1 and YA2, wherein YA1 existing at Z1 is equal to 0.2 meters is our region of the highest concentration. The maximum concentration, or the highest concentration of TCE in this case, is dependent on the vapor pressure of TCE. Okay? So we are already given the vapor pressure of TCE here. If you divide the vapor pressure with the total pressure, you get the mole fraction of TCE at Z1. Here we have another representation of the problem. Our given diffusivity is 0.088 square centimeter per second. We simply have converted that to square meter per second. So that is now 8.8 times 10 raised to negative 6. Now, just by looking at the illustration, we can already tell that this problem is a unimolecular diffusion problem. That's because our air inside of the drum is stagnant and TCE is the only diffusing species. Remember that TCE is diffusing from Z1 to Z2. Okay? Now that we know that this problem is unimolecular diffusion, we can use one of our previously derived equation to solve this problem. We have the molar flux of TCE, that is NaZ, is equal to C DAB over Z multiplied by ln of 1 minus XA2 over 1 minus XA1. Now, this derived equation previously was for liquid systems. Since we now have a gaseous system, we simply have to change our form of concentration. For liquid systems, we use C for concentration and X for mole fraction. While for gaseous systems, our concentration is expressed in terms of pressure. That is, C is equal to P over RT. And our mole fractions for the gaseous phase will be represented by Y. Okay? This is to avoid confusion between X and Y. So our new equation accounting for our gaseous system is now NaZ is equal to total pressure multiplied by DAB over Z times R times T multiplied by ln of 1 minus YA2 over 1 minus YA1. We have previously determined that our YA2 is equal to 0. That is because we are assuming that as your TCE makes its way at the opening of the container, it is being swept away by the outside air. Okay? And our YA1 is simply the vapor pressure divided by the total pressure. YA1 has a value of 0.1520. Our Z in this case is actually delta Z. Our delta Z is simply Z2 minus Z1. That is 5 meters minus 0.2 meters equal to 4.8 meters. Substituting given values to our new derived equation, we have total pressure, atmospheric pressure, we have 101,325 pascals times the diffusivity, 8.8 times 10 raised to negative 6 divided by our delta Z is 4.8 meters times R, 8.314 multiplied by our absolute temperature, that is 35 degrees Celsius plus 273.15 to make it Kelvin. And that is multiplied to ln of 1 minus 0 at the top is 1 over 1 minus YA1 is 0.1520. Our molar flux in this case has a value of 1.195 times 10 raised to negative 5. The units of this is moles per second per square meter. Remember that this is still molar flux. And molar flux is the rate of transports over the area of transfer. Okay, now since this is still expressed as a molar flux, to answer the question, are we emitting more than 1 kilogram per day of TCE? The answer to that is we have to convert our molar flux to the rate of transfer. Remember that the molar flux is equal to the rate over the area of transfer. The area of transfer in this case is the cross-sectional area of our cylinder. Therefore, we solve that as pi over 4d squared. Our degreaser has a diameter of 2 meters. Therefore, we can easily solve for its cross-sectional area. So we can now say that our rate of transfer is simply equal to our flux, our molar flux, multiplied by the cross-sectional area. So we have here our molar flux. I'm going to multiply that with pi over 4 times diameter squared, that is 2 meters squared. Our rate of transfer is 3.76 times 10 raised to negative 5 moles per second. Since our rate now has units of moles per second, we simply have to convert that to kilograms per day in order for us to determine if we are still within the allowable limit. Okay? Converting moles to kilograms, our molecular weight is given. So we have 131.4 grams of TCE per mole. And then we simply convert from grams to kilograms. And then we will be converting from seconds to days. So there are 3,600 seconds per hour. And then there are 24 hours per day. Okay, if we execute that, we will be able to know the rate of evaporation of the TCE. So we have 3.76 times 10 raised to negative 5 moles per second multiplied by 131.4 divided by 1,000 times 3,600 times 24. Our rate of evaporation is 0.43 kilograms of TCE per day. This means that we are still well within the limit of 1 kilogram per day. That means that we are not violating any regulation. Okay, so this figure that we have determined, 0.43 kilograms per day, takes into account that we are only assuming unimolar diffusion and there is no convective mass transfer happening in this case. Okay, if there is convective mass transfer involved, this rate of transfer will be higher because convective mass transfer is associated with higher rates of mass transfer. We will be tackling convective mass transfer in a separate video. Let's try to solve other examples. We have two very large tanks maintained at 323 Kelvin and 1 atmosphere total system pressure are connected by a 0.1 meter diameter circular duct which is 5 meters in length. Tank 1 contains a uniform gas of 60 mole percent acetone and 40 mole percent air, whereas Tank 2 contains a uniform gas of 10 mole percent acetone with 90 mole percent air. Determine the initial rate of acetone transfer between the two tanks. This is our given for the problem. So we have the two tanks containing different mixtures of acetone and air connected by a pipe 5 meters in length and 0.1 meter in diameter. we are required to solve for the molar flux of acetone. Okay, so we will be representing acetone as letter A and air as letter B. So we now have the values of Ya1, Ya2, Yb1, and Yb2. Those are the mole fractions of acetone in air at the two ends of the connecting pipe. Our system temperature is at 323 Kelvin, and the total system pressure is 1 atmosphere. Now, based from this given, you would see that this is an example of an equimolar counter diffusion problem because there is nothing preventing both acetone and air from diffusing to both tanks 1 and 2. If you notice on tank 1, you have a high concentration of acetone but a low concentration of air. In tank 2, you have a high concentration of air and a low concentration of acetone. So what would happen is there will just be an exchange of acetone and air, wherein acetone, or letter A, will travel from tank 1 to tank 2, and then air, or letter B, will travel from tank 2 to tank 1. Okay, so they are both diffusing, therefore this is equimolar counter diffusion. And earlier we have derived our simplified equation for equimolar counter diffusion. We have the molar flux NAZ is equal to negative C dAB times dXA over dZ. But then again, we are dealing with gases, so it's very important for us to convert our concentration in terms of pressure. So we have C is equal to P over RT, and we simply replace X sub A with Y sub A. Okay, our new equation is now NAZ is equal to P dAB over RT times dYA over dZ. Our P here is P sub T, or the total pressure of the system. We simply substitute the given in this derived equation. However, we don't have yet a value of the dAB, or the diffusivity of the system. Remember that dAB is a very particular value that depends on the components of the system. In this case, our components are acetone and air. We can say that acetone is diffusing through air, or air is diffusing through acetone, because this is equimolar counter diffusion. Now let's look for the value of the diffusivity. You can find the values of diffusivity for pairs of gases in your handbook. We have here table 2-324 of the 8th edition of Paris Chemical Engineers Handbook. We have the diffusivities of pairs of gases and vapors at 1 atmosphere. You simply need to look for your diffusing species. In this case, our diffusing species is acetone, and it is diffusing through air. If you locate the value, that is acetone air, the value is 0.109 square centimeter per second. But it is important to note that the value 0.109 is only valid at 0 degrees Celsius. Our system temperature is 323 Kelvin. Therefore, we have to convert this value of diffusivity to an appropriate value at our system temperature. Okay, let me first list 0.109 square centimeter per second at 0 degrees Celsius. Going back, our conversion equation is simply a ratio and proportion. We write D1 P1 over T raised to 1.75 is equal to D2 P2 over T2 times 1.75. D represents the diffusivity, P the pressure, and T the absolute temperature. So using this analogy, we can determine our new diffusivity, that is D2, and that is equal to D1 multiplied by P1 over P2 multiplied by T2 over T1 raised to 1.75. Since the given pressure in the table is 1 atmosphere and our system pressure here is 1 atmosphere as well, we no longer need to convert the pressure. What we need to convert is our diffusivity in terms of the temperature. Okay, so solving for D2, we have D1 0.109 square centimeter per second multiplied by the ratio of the temperatures. T2 is our system temperature, that is 323 Kelvin, and then T1 is the temperature in the table from your handbook, that is 0 degrees Celsius or 273.15 Kelvin, and this ratio is raised to 1.75. Our new diffusivity is 0.146 square centimeter per second. Let's now convert this to square meters per second. You simply divide this by 100 squared. This is now in square meters per second. Therefore, the value of our diffusivity DAB is equal to 1.46 times 10 raised to negative 5 square meter per second. This is now at a temperature of 323 Kelvin, and this is what we are going to use for our calculations. Going back to our molar flux equation, we simply have to integrate this expression in order to get our final expression. So we now have negative total pressure dAB over RT times YA2 minus YA1 divided by Z2 minus Z1 or delta Z. Okay, substituting, we can now solve for NAZ. That is negative pressure 101,325 pascals. dAB, which we have determined earlier, that's 1.46 times 10 raised to negative 5 square meter per second, multiplied by R, 8.314, and temperature of 323 Kelvin. That is multiplied by YA2 minus YA1, 0.1 minus 0.6, divided by delta Z, which is 5 meters. Okay? Our flux is equal to 5.509 times 10 raised to negative 5. The unit of this is, again, mole per square meter per second. That is rate over area. We now have our molar flux of transfer. Let's determine the rate of transfer. So let us add that to our required, the rate of mass transfer. The rate of transfer in this case would be similar to what we have done earlier, in which we simply multiply the flux or the molar flux with the cross-sectional area of the conduit. In this case, this is again a cylinder. Our connecting cylinder has a cross-sectional area of pi over 4 times d squared. We know the diameter of the pipe to be 0.1 meters, so we can simply solve for the rate RAZ as the molar flux NAZ 5.509 times 10 raised to negative 5 moles per square meter per second multiplied by pi over 4 times diameter squared 0.1 squared. Our rate of transfer is now 4.33 times 10 raised to negative 7 moles per second. We now have determined both the flux of transfer and the rate of transfer. That shows you the basics of steady-state diffusion. For our next video, we'll be discussing unsteady-state diffusion. Please do watch out for separate videos detailing the solutions for other problems involving steady-state diffusion. Okay? That's it for this lesson. Thank you for listening. I hope you have learned something, and as always, keep safe.